Hello there. My name is Alara, and welcome to the Late Night Science Channel. Tonight we're going somewhere quiet, somewhere vast. We're going to ask one of those questions that feels simple at first, almost childlike, but the deeper you sink into it, the more it stretches, like space itself. Does space end? Does it stop somewhere? Is there a wall, a border, some final curtain where everything just finishes? And if you enjoy content like this, something calm, something to help you unwind while your mind gently explores the cosmos, I'd really appreciate it if you hit that like button. It helps more than you might think. Subscribe if you haven't already, and let me know in the comments where you're watching from and what time it is for you right now. I love hearing from all of you, scattered across the globe like stars in a galaxy. Now, let's begin. So, what is space, really? When you look up at the night sky, you see darkness, right? Black canvas dotted with stars. Most of us think of space as nothing, a void, an empty place where planets float and stars burn. But that's not quite accurate. Space is far from empty. In fact, it's one of the most misunderstood, most active parts of reality. For a long time, people thought space was simple, just a backdrop, like a stage in a theater where actors, stars, and planets moved around. This idea came mostly from Isaac Newton. He believed space was absolute, fixed, unchanging, a three-dimensional grid that just sat there while everything happened on top of it. Time ticked along the same for everyone, everywhere. Space was just the place where it all occurred. Then Einstein came along. Wild hair, chalkboards covered in symbols, and a mind that bent reality itself. He showed us something strange, something elegant. Space isn't passive at all. It's alive. It's a fabric, one that bends and stretches and warps when mass and energy are nearby. Space and time together form something called spacetime, and this fabric actually responds to what's happening in it. Picture a trampoline. Place a bowling ball in the center and the fabric dips down, creating a curve. Now roll a marble across the surface. Instead of going straight, it curves around the dip. That's how gravity works in Einstein's universe. Massive objects like stars and planets bend space-time around them. We don't fall toward Earth because it's pulling us like a magnet. We fall because Earth has warped the fabric of space-time, and we're rolling into that dip. Now, you might think, okay, fine, space bends, but when there's nothing in it, when we're looking at the empty gaps between stars, isn't that just nothing? Not quite. Even in the darkest, loneliest corners of the universe, space is buzzing with activity. Thanks to quantum mechanics, we now know that empty space isn't truly empty. At the smallest scales, far tinier than atoms, space is humming with what physicists call quantum fields. These fields aren't things in space. They are space in a way. Every particle in the universe comes from its corresponding field. An electron from the electron field, a photon from the electromagnetic field. Even when no particles are present, these fields never stop fluctuating. They produce tiny, fleeting particles that pop into existence and vanish almost instantly, like cosmic fireflies. This jittery energy is called vacuum energy. It's like the surface of a pond. From far away, it looks calm, smooth, but get close and you see ripples, little disturbances, the occasional splash. What seems empty from a distance is actually full of hidden motion. That's why physicists say the vacuum isn't empty, it seethes with potential. Virtual particles appear and disappear in pairs, too quick to observe directly, but their effects can be measured. They influence how electrons behave, and they even contribute to something mysterious called dark energy, which seems to be pushing the universe apart faster and faster. So no, space isn't just the place where things happen. Space is one of the things that happens. And maybe that's the strangest part of all. The more we study it, the more it refuses to be empty. It twists, it hums, it fluctuates, it expands. Even when it seems to do nothing, it's never really doing nothing at all. Now, imagine standing on a hilltop under a clear night sky. The stars stretch out in all directions. It feels endless, doesn't it? Infinite, eternal. But there's a cosmic limit to what you can see, a kind of bubble that surrounds us. Not because the universe ends there, but because light simply hasn't had time to reach us from the beginning of time. This is the observable universe. It's the part of the cosmos we can actually detect. Light, radiation, anything that's managed to travel to us since the beginning of time. That word, observable, is key. It doesn't mean everything outside of it doesn't exist. It just means we haven't been lucky enough to see it yet. You might think the farthest we could see would be about 13.8 billion light-years away. After all, that's how long the universe has been around. And if light moves at the speed of light, wouldn't that be the edge of our vision? Ah, if only it were that simple. Because of the way space itself expands, that boundary is actually much farther out. The observable universe has a current radius of about 46.5 billion light-years in every direction. That makes it roughly 93 billion light-years across. Yes, even though the universe is only 13.8 billion years old, the distance to the farthest galaxies we can see is more than 3 times that. Why? Because space has been stretching the whole time. Think of it like this. Imagine raisins on a loaf of bread, and you put it in the oven. As the bread rises, the raisins move farther apart. Now imagine a photon of light is emitted by one raisin toward another right as the baking begins. By the time the light arrives, the bread has expanded. The photon didn't travel across a fixed distance, it traveled across a growing one. The destination moved farther away while the light was on its way. That's what happens on a cosmic scale. This brings us to the cosmic horizon. It's not a wall. You're not going to fly a spaceship out there and bonk into the edge of the universe. It's more like a gentle fading of information. Beyond this horizon, light from distant regions hasn't had enough time to reach us since the Big Bang. It's as if we're standing in a vast fog, only able to see nearby glows. The rest is shrouded, not because it's not there, but because the universe hasn't given us the signal yet. This horizon forms the boundary of our observable universe, and it's always changing. As time goes on, light from more distant regions arrives, and the bubble expands. At the same time, because of the accelerating expansion of space, some galaxies are moving away from us so quickly that the light they emit now will never reach us, not even in trillions of years. They're receding faster than light itself, not because they're breaking any cosmic speed limit, but because the space between us is stretching too fast. In a very real sense, the universe is slipping out of our grasp. Every single star, every galaxy, every smudge of light we see in the night sky is within our observable universe. That's the good news. The not-so-good news, there's almost certainly far more beyond it, maybe infinitely more that we'll never see, touch, or study. We're surrounded by vastness that mocks our instruments, and yet we can only peek through this little bubble of perception. What's even more humbling is that everyone, everywhere, has their own observable universe. If you were standing on a distant galaxy 10 billion light-years away, your cosmic bubble would overlap ours a bit, but it would also include regions we'll never know. In other words, the observable universe isn't the universe, it's just our slice of it. And what a slice! Roughly 2 trillion galaxies, each containing millions to trillions of stars. That's a lot of starlight crammed into our little observational bubble. The photons from some of these galaxies have been traveling for billions of years, only to finally be absorbed by your eye or your telescope. Tonight, some of that light began its journey before Earth had even formed. That ancient glow is a kind of time machine, a message in a bottle from an epoch long past. And yet, as rich as this observable universe is, it may represent only a tiny fraction of the total universe. Beyond the cosmic horizon, space might continue forever. It might be curved or flat or loop back on itself in some strange geometry. But we'll never know. Not with light, not with any signal bound by time and the speed of light. There's a kind of peace in that limit. Knowing we can't see everything reminds us that our place in the cosmos is fundamentally local. We don't have to understand or control the whole universe to find meaning in it. Sometimes it's enough to sit beneath the stars and know you're part of something much larger than yourself. When we look up at the night sky, we often imagine we're seeing the universe as it is right now. But that's not true. What we're really seeing is the universe as it was. Every star, every galaxy, every glowing dot is a time capsule. The farther away it is, the older the light we're seeing. Looking across the universe is like rummaging through a cosmic attic. Each layer of light takes us deeper into the past. Let's start with the light year. A light year is the distance light travels in 1 year, about 6 trillion miles. When you look at a star that's 100 light years away, the light reaching your eyes left that star 100 years ago. You're seeing it not as it is, but as it was when your great-grandparents were young. Now stretch that idea across space. Some galaxies we observe are billions of light years away. That means the light we detect from them began its journey before our solar system even existed. Long before Earth formed oceans or developed its first life, that ancient glow was already racing toward a future observer, toward you. This leads us to something astronomers call look-back time. It's a way of expressing how far into the past we're seeing when we observe distant objects. If a galaxy is 8 billion light-years away, its look-back time is 8 billion years. That light has been traveling for more than half of the age of the universe, arriving just in time to land on your telescope or illuminate your evening stargazing. In a strange way, space is full of ghosts, echoes of what once was. We're not seeing galaxies as they are today. We're seeing them frozen in earlier chapters of their existence. Some of them may not even exist anymore. They might have merged with other galaxies, changed shape, run out of gas, or drifted beyond the reach of light. What we see is a kind of cosmic fossil record, written in photons. But it gets even more fascinating. As light travels through the expanding universe, it stretches. This is known as redshift. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelength of light lengthens when its source moves away. Since space itself is expanding, nearly all distant galaxies are receding from us, and the light they emit becomes stretched into longer, redder wavelengths as it travels, hence the name redshift. By measuring the amount of redshift in the light from a galaxy, astronomers can determine how far away it is, and more importantly, how long that light has been on its journey. A high redshift means a very distant galaxy and a very ancient glimpse into the early universe. This redshifted light holds clues about the structure, age, and history of the cosmos. It tells us how fast the universe is expanding, how galaxies evolve, and even hints at mysterious forces like dark energy that are shaping everything on a grand scale. Every photon is a little messenger from the past, carrying encoded stories of where it came from and what the universe was like back then. Now let's talk about telescopes, our cosmic time machines. When you look through a telescope, you're not just seeing things more clearly, you're seeing them more deeply into time. A backyard telescope might show you Jupiter's clouds from about 40 minutes ago. A more powerful observatory could show you a galaxy as it appeared 500 million years ago, back when life on Earth was still experimenting with fins and gills. Then we have the heavy hitters, observatories like Hubble, James Webb, and future successors waiting in the wings. These instruments can peer so far into space, and thus so far back in time, that they capture the faint light of the first galaxies to ever form. We're talking about structures that began taking shape just a few 100 million years after the Big Bang. It's a little ironic. In our quest to understand the future of the universe, we spend most of our time staring into its past. But that's the nature of light. It travels fast, but not instantly. And because the universe is so vast, even light has to work hard to keep up. This means the universe, as we experience it, is always a little out of date. It's like watching a film still being edited, with scenes arriving one at a time, out of order. Some from galaxies just next door, others from across the cosmic abyss. Yet that delay is a gift. Without it, we'd never be able to piece together the story of how everything came to be. The slower arrival of ancient light lets us see different stages of the universe's evolution all at once, like pages torn from a novel and scattered across the sky. The result is a kind of beautiful patchwork of time. In one direction, we might see a relatively nearby galaxy that formed recently. In another, we might glimpse flickering light from billions of years ago, when stars were still forming from clouds of primordial gas. All of these images are layered not just across space, but across time itself. You could say we're living inside a museum made entirely of light. But instead of walking from exhibit to exhibit, we let the photons come to us, crossing unimaginable distances to tell their stories, to fill our sky with ancient news from the dawn of everything. There's something quietly poetic about this. Every time you look up, you're gazing into a time machine. The light brushing against your eyes may have started its journey before the first tree on Earth, before the first cell, before the first breath of atmosphere. And all of this comes from simply listening to the light. By studying its colors, its shifts, its age, we unlock a silent language spoken across billions of years. A language that doesn't just describe the universe, it is the universe, encoded in motion and memory. Next time you see a star twinkling above, remember you're not looking at it as it is. You're looking at a version of it preserved in time, a glimmer of history still racing through the darkness. You're seeing what the universe looked like when it was younger, smaller, perhaps even gentler. And through the lens of science, with the patient help of light, we continue to piece together our origin story, one distant glow at a time. Picture yourself standing in a field early in the morning. The grass is wet with dew, the air is cool, and a soft fog rolls across the horizon. You can only see a short distance ahead, maybe a few trees, the outline of a hill, but beyond that, everything fades into a pale blur. You know the world continues past the fog, but your vision can't reach it just yet. In a way, that's what it's like to live inside the universe. No matter how powerful our telescopes become, there's a limit to how far we can see. Not because of fog in the traditional sense, but because of time, distance, and the peculiar nature of the expanding cosmos. These limits are what we call cosmic horizons. They define the boundaries of our observable universe. Unlike the tidy horizon on Earth, where sky meets land, cosmic horizons come in different flavors, each with its own rules and significance. The first is called the particle horizon. Think of it as the maximum distance from which light or any other signal could have reached us since the universe began. It marks the outermost edge of our observable universe, the ultimate limit of our current cosmic bubble. The particle horizon is shaped by time itself. Since the universe has existed about 13.8 billion years, and because space has been expanding during that time, the furthest distance light could have traveled to reach us today is around 46 billion light-years in any direction. That's why the observable universe is roughly 93 billion light-years across. It's the grand perimeter of everything we can currently detect. But don't mistake this horizon for a wall. There's no border, no glowing edge. Instead, it's a limit woven into the fabric of time. Like standing on the shore of a vast sea, you can look out as far as light allows, but you'll never see beyond that gentle curve. Not because there's nothing there, but because the signals haven't had time to arrive. Next, we come to the event horizon of the universe, not to be confused with the dramatic kind surrounding black holes. In cosmology, the event horizon refers to the boundary beyond which events can never affect us no matter how long we wait. It's the cosmic line in the sand. Anything beyond this point is retreating from us faster than the speed of light due to the expansion of space. That light, no matter how persistent, will never catch up to us. It's like trying to send a message to a friend on a raft floating away down a river. You throw a bottle with a note inside, but the current is so strong that the raft drifts faster than the bottle can reach it. That's the event horizon, where communication, even light itself, becomes impossible. At this very moment, the cosmic event horizon is thought to be around 16 billion light-years away. That means there are regions of the universe we can see now, but if those regions emit new light today, that light will never reach us. We're watching galaxies that are, in a very real sense, slipping away, visible today, but destined to fade from view forever. Finally, we have the cosmological horizon, which is sometimes used interchangeably with the particle horizon, but can also refer to more general boundaries in spacetime. It's a term that encompasses these observational limits and reminds us that horizons aren't just visual, they're deeply tied to the physics of the universe itself. These horizons are constantly shifting and evolving. As the universe ages, the particle horizon grows. More light has time to reach us. But because of dark energy and the accelerated expansion of space, the event horizon shrinks in relevance. More galaxies move beyond our reach. The universe becomes a place of increasing isolation, not because it's empty, but because the light from its distant corners is falling behind. To put it another way, the universe is like a slowly inflating balloon. Dots on its surface drift apart, and the farther they are, the faster they move away. We can only see the dots close enough for their light to make the trip. Beyond that, the light stretches and dims until it vanishes into the expanding abyss. There's something haunting but also peaceful about these limits. It's a quiet reminder that we're not all-knowing observers. Our view is shaped by cosmic history, by how long light has been traveling, and by the strange properties of the space it travels through. We're peeking through a window that's enormous, yes, but still finite. Some regions of the universe will always remain a mystery, no matter how patient or clever we become, not because we lack technology, but because of the very nature of space-time itself. These unseen realms aren't behind a curtain waiting to be pulled back. They are beyond the reach of information, forever unknowable. And yet, even within these boundaries, we've managed to learn so much. We've mapped galaxies, measured background radiation, traced the fingerprints of the Big Bang. We've used the fog of the particle horizon to understand the structure of the cosmos and the glow of ancient light to piece together its story. The horizons don't limit our imagination, they frame it. Like the rising sun burning off morning mist, every new discovery pushes the fog back just a little, revealing more of the landscape. But some parts will always remain hidden behind the curve, behind the stretching boundary where light will never arrive. Still, here we are, spinning quietly in a corner of the universe, watching photons arrive from billions of years ago, reading the messages they carry, dreaming about what lies beyond the next soft bend in the cosmic road. Even if we can't see it all, even if parts of the universe are forever beyond our reach, the beauty is in the trying, in listening to the quiet hum of light, in following it to the edges of knowledge, and in knowing that while we may never see the full view, we're part of the story just the same. Not too long ago, in the grand timeline of human curiosity, people believed the universe was pretty steady. Galaxies were out there, stars were shining, and everything, more or less, stayed put, a quiet, eternal cosmos. But in the early 20th century, a game-changing discovery quietly rose from a mountaintop observatory, and the universe hasn't sat still since. It was Edwin Hubble, yes, the same name we gave the famous space telescope, who first noticed something peculiar. While studying distant galaxies, he observed that their light was consistently redshifted. That meant the galaxies were moving away from us, and the farther away they were, the faster they seemed to recede. This wasn't random, it was a pattern, a law. Space itself, it seemed, was expanding. Now, this isn't quite the same as galaxies zooming through a fixed space, like cosmic race cars. It's not like they're bursting outward into a pre-existing void. What's actually happening is stranger and more elegant. Space itself is growing. Imagine space as the thing stretching, and galaxies are being carried along with it, like raisins embedded in rising bread. That image, raisin bread, is a gentle and surprisingly accurate way to picture it. Think of the dough as space and the raisins as galaxies. As the dough bakes and rises, it stretches in all directions. Each raisin finds itself farther from the others, not because it's moving on its own, but because the dough between them is expanding. There's no central raisin, no preferred direction, just a uniformly growing loaf. This is how the universe works on a large scale. Galaxies aren't rushing outward through space, they're being carried away from each other as the fabric of space itself stretches. That's why no matter where you are in the universe, it looks like everything else is moving away from you. From every galaxy's point of view, space is expanding in all directions. It's a bit like being in a rising souffle. No matter which bubble you're in, all the other bubbles seem to be drifting away. The universe isn't expanding into anything, it's just expanding. There's no outer shell, no edge it's racing toward. The distances between unbound objects simply grow over time, as if the cosmic measuring tape is slowly lengthening. This idea of an expanding universe was so radical when Hubble proposed it that even Einstein had to revisit his own equations. Originally, Einstein had added something called the cosmological constant to his theory of relativity to make the universe stand still. He thought the cosmos had to be static, and his equations, left to their own devices, suggested otherwise. When he heard about Hubble's findings, he famously called the addition of the constant his greatest blunder. Though, ironically, the concept has since made a comeback in explaining dark energy. The universe has a sense of humor, it seems. But back to the expansion. One of the most beautiful consequences of Hubble's discovery is that it allowed us to rewind the cosmic clock. If galaxies are all moving away now, they must have been closer together in the past, much closer. This led scientists to the idea of a hot, dense beginning to the universe, what we now call the Big Bang. The term Big Bang can be a little misleading. It wasn't an explosion in space like fireworks going off in a dark field. It was more like the rapid swelling of space itself, everywhere, all at once. No center, no blast radius, just the entire universe suddenly stretching out of a state of extreme density and heat. You can't point to a location in the sky and say that's where the Big Bang happened, because it happened everywhere, including right where you're sitting. That expansion is still going on today, nearly 14 billion years later. Galaxies continue to drift apart, and the light they emit continues to stretch with them. The farther away something is, the more its light gets redshifted by the expanding universe. It's a cosmic stretching of time and space that shapes every observation we make. Interestingly, the universe's expansion doesn't affect everything equally. It works on the grand scale, between galaxies and galaxy clusters, but it doesn't pull your morning coffee farther from your lips or separate the atoms in your chair. That's because gravity and other forces dominate on smaller scales, keeping things nicely glued together. The Milky Way isn't expanding. Your neighborhood definitely isn't expanding. And unless your washing machine is eating socks again, even your laundry pile is relatively stable. But on the cosmic level, the expansion continues. And what's more, it's accelerating. This discovery, made in the late 1900s, came as a surprise. Scientists had assumed the expansion might be slowing down due to gravity. Instead, they found that some mysterious force, now called dark energy, is causing it to speed up. The dough isn't just rising, it's rising faster and faster with every passing moment. No one's entirely sure what dark energy is. It might be an inherent property of space itself, or a field we haven't understood. But whatever it is, it now dominates the energy budget of the universe. That gentle stretch is turning into a cosmic sprint, and galaxies are receding from one another at ever greater speeds. It's a little poetic in a quiet way. The universe began with everything close together, dense and unified. Over time, it expanded, cooled, formed stars and planets, all the ingredients for life. And now it continues to drift outward. Stars aging, galaxies moving apart, space stretching into the unknown, like a story that opens with intensity, blossoms into complexity, and drifts off into a gentle, infinite epilogue. There's no sound in space, but if there were, maybe it would be the soft creak of rising dough, the occasional pop of a bubble, the slow shift of warm expansion. Not a violent noise, not a shout, just the peaceful hum of a universe becoming itself. So when we say the universe is expanding, we're not talking about things flying away from some central point. We're talking about the very fabric of reality stretching as calmly and steadily as a loaf of bread in the oven. It's one of the most profound discoveries in science, and also one of the most comforting. The idea that change can be slow, steady, and beautiful. And as we sit here, surrounded by stars and bathed in ancient light, we're part of that expansion. Every breath, every heartbeat, every thought you've ever had has taken place on a little rock spinning in the middle of rising cosmic dough. It's enough to make you hungry for answers, or at least for a midnight snack. In physics, there's a hard rule that's never meant to be broken. Nothing can move faster than light. Not a spaceship, not a signal, not even the fastest runner in the world. According to Einstein's theory of relativity, the speed of light, about 299 million meters per second, is the universal speed limit. Nothing with mass can ever reach or exceed it. And yet, out there in the great cosmic distance, astronomers have observed something that seems to defy this rule: galaxies that appear to be moving away from us faster than the speed of light. Entire clusters of stars and dust slipping beyond our grasp at what seem like impossible speeds. It sounds like physics should be panicking, but don't worry, everything's fine. The universe isn't breaking the rules, it's just playing a very clever game with them. To understand what's going on, we need to revisit a key idea. Galaxies are not flying through space like comets in a vacuum. Instead, space itself is expanding, and galaxies are being carried along with it. Think of space as a rubber sheet with dots on it. If you stretch the sheet, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is growing underneath them. This is how galaxies can appear to recede from each other faster than light. It's not that they're breaking the speed limit, it's that the space between them is stretching so quickly that the total separation increases at a rate that light can't bridge. The galaxies themselves remain obedient citizens of physics. It's space that's doing the heavy lifting. Here's a helpful way to picture it. Imagine you're standing on a treadmill that's gradually speeding up. You try to walk towards someone at the other end, but the treadmill is moving backward faster than you can walk forward. Eventually, no matter how hard you try, the distance between you and the other person keeps increasing. It's not that you're walking too slowly, it's that the ground beneath you is working against your motion. In the case of the universe, light is trying to travel through expanding space. But in some regions, especially very far away, space is expanding so rapidly that the light never makes progress towards us. It's like trying to paddle a canoe upstream during a flash flood. The water flows too fast, and your boat is swept farther away despite your best effort. This doesn't violate relativity because that theory only forbids objects moving through space faster than light. It doesn't say anything about how fast space itself is allowed to grow. And it turns out, space has quite a flair for dramatic entrances. Take, for example, a period called cosmic inflation. This was a mind-bendingly brief moment just after the Big Bang, when the universe expanded at an absolutely staggering rate, far faster than the speed of light. In less than a trillionth of a second, the universe grew from something smaller than a proton to something the size of a grapefruit, or possibly larger. Try explaining that expansion in a recipe. And again, this faster-than-light swelling didn't break any rules. It was space doing the expanding, not particles racing through it. It's one of the few times in physics when faster-than-light travel is not only allowed, but encouraged. Just don't try it in a spaceship. Your engines will not appreciate the suggestion. This rapid inflation smoothed out the early universe, ironing away wrinkles and unevenness like a steam press. It also helps explain why the universe looks so uniform in every direction, despite that distant regions haven't had time to exchange information. Inflation spread everything out so quickly that local differences became subtle and stretched far apart. Even now, billions of years later, we're still seeing the effects of that expansion. Space continues to grow, carrying distant galaxies farther and farther away from us. Some of those galaxies are now receding faster than light, not because they're speeding up, but because the space between us is growing faster than light can close the gap. This means there are regions of the universe we can never see. No matter how long we wait, their light will never reach us. And if they emitted new light today, that light would be swept away into the deepening void. These galaxies aren't lost because they're moving too fast. They're lost because the road between us is stretching out faster than their signals can travel. It's a bit like trying to send a postcard across a river where the opposite shore is drifting away faster than you can throw. No matter how many stamps you stick on it, the postcard is never going to make it. Eventually, even the idea of delivery becomes meaningless. So when astronomers say some galaxies are receding faster than light, what they mean is this. Due to the expansion of space, the separation between us and those galaxies is increasing at a rate that light can't keep up with. There's no violation, no rebellious physics, just a clever interpretation of how space and time can flex in ways our instincts don't always understand. In fact, this cosmic trick has another strange consequence. There are galaxies we can see today, clear as day through our best telescopes, that have already crossed this horizon. They're still visible because the light they emitted long ago is still arriving, but their newer light, being produced now, is already out of reach. It will never get to us, not even if we wait an eternity. It's a little like watching the taillights of a car that's just turned a corner. You can still see the glow, but the car itself is already gone, cruising down a road you'll never follow. The light is a ghost, a message from a past that can no longer be updated. This reality has a certain peaceful melancholy to it. The universe is full of stories we'll never hear, stars we'll never see, galaxies we'll never know existed, not because we didn't look hard enough, but because the cosmos itself is drawing the curtain, stretching the stage beyond our view. Yet this too is part of the wonder. The fact that we've been able to glimpse so much of the universe's past is nothing short of miraculous. Despite all the distance and distortion, we've still managed to see billions of light years in every direction. We've caught ancient photons in mid-flight, pieced together the origins of galaxies, and even traced the faint afterglow of the Big Bang itself. And all of this has happened from a tiny planet orbiting an unremarkable star in an average galaxy, in a universe where space moves faster than light. It's enough to make you feel small, but also strangely lucky. Because here we are listening to the whispers of an expanding cosmos, watching light struggle to reach us, counting galaxies as they fade into the distance. And all the while, the dough of the universe continues to rise, carrying with it the dreams of curious beings who once wondered just how far light could go. When we think about the universe, it's tempting to picture it like a big box, a vast rectangular space with a top and bottom, left and right, front and back, just floating in something. Maybe it has edges, maybe it goes on forever. Maybe there's a giant cosmic wall with a "Do Not Enter" sign and a very bored security guard. But the real shape of space is much more subtle, much more fascinating. It turns out that space isn't necessarily flat like a tabletop. It might be curved. In fact, it might be positively or negatively curved, or just ever so gently flat. And this isn't just a matter of aesthetics. The geometry of the universe has deep implications for how it evolved, how it behaves, and whether it might one day curve back in on itself or continue stretching forever. Let's start with the three main possibilities. The first is a flat universe, like an infinite sheet of paper. In this model, the rules of geometry behave just as we learned them in school. Parallel lines never meet. Triangles always add up to 180 degrees, and if you travel in a straight line, you'll never loop around. You'll just keep going indefinitely through an endless cosmic plane. The second option is a closed universe, shaped like a sphere, or more precisely, the three-dimensional equivalent of a sphere. Here, space curves back on itself, like if you were to set off in a straight line in any direction and somehow avoided stars, planets, and all other space debris, you would eventually return to your starting point. Like walking in a straight line around the surface of Earth, you wouldn't fall off, you'd just keep going in circles, though it might take several billion years and a very sturdy pair of shoes. The third possibility is an open universe, shaped like a saddle. This space curves outward. In this geometry, parallel lines eventually diverge. triangles add up to less than 180 degrees, and if you tried to go around the universe, you'd never come back to where you started. You'd simply drift farther and farther out into cosmic vastness. These shapes, flat, closed, and open, aren't just abstract ideas. They're tied directly to the universe's overall density and energy content, specifically how much matter and energy exist compared to what would be needed to make the universe perfectly balanced. This critical density determines whether space bends inward, outward, or not at all. It's a bit like a cosmic balance, not too much, not too little, but just enough to keep the geometry straight. And how do we measure this? As it turns out, the universe leaves behind clues in the cosmic microwave background, the ancient light that's been traveling since shortly after the Big Bang. By analyzing the tiny fluctuations in this faint glow, scientists can determine how space bends light over vast distances. It's like using the pattern of ripples on a pond to understand the shape of the shore. So far, the evidence suggests something remarkable. Our universe appears to be very, very close to flat. Not perfectly flat, perhaps, but close enough that any curvature is too small to detect with current instruments. It's like standing on a massive plane that might have a slight bend somewhere over the horizon, but as far as you can see, it's pretty straight. Now here's where things really get interesting. A flat universe can still be infinite or not, and a closed universe, surprisingly, can be finite but unbounded. That phrase sounds like a contradiction at first, like saying you have a cup that's full but holds nothing, but it makes sense with a little thought. Take the surface of a sphere. It's finite. You can measure the total area, but it has no edges. You can walk around the surface of a globe forever and never fall off the edge, because there is no edge. The whole surface connects back on itself. Now take that concept and apply it to a three-dimensional version. That's what cosmologists mean by a space that's finite but unbounded. It's a closed loop, a self-contained bubble of geometry. This kind of space doesn't have a border. There's no place where the universe ends and something else begins. It's just space curving back around in a grand, subtle loop. And because we live within it, we'd never be able to tell directly. We'd just keep drifting forward, thinking we're going straight, while quietly bending back to home. Even in a flat or open universe, infinity brings its own peculiar flavor. An infinite universe means an endless number of galaxies, stars, and potentially even repeating patterns. Somewhere out there, if the universe is truly infinite, there could be another version of you listening to this same video, possibly wearing slightly different pajamas. Now, it's worth noting that we can only observe a small fraction of the universe. Beyond our observable horizon, we don't know how space behaves. It could be flat forever, or it could curl into a loop we're too small to detect. The curvature might be so slight that even a light beam traveling for billions of years doesn't reveal it. It's like trying to tell Earth is round while standing in a meadow. You don't see the curve, but it's there all the same. Cosmic geometry also affects the fate of the universe. In a closed universe, gravity might eventually slow down the expansion and cause everything to contract, leading to what's called a big crunch. In an open or flat universe, expansion could continue indefinitely, thinning out matter and cooling the cosmos into a gentle fade. Though with dark energy pushing things apart ever faster, the big crunch seems unlikely, at least with what we know today. What's particularly comforting, in a quiet kind of way, is that no matter the shape, we're part of it. Whether the universe loops or drifts, curves or stretches, we are woven into its structure. Our atoms obey its geometry. Our light traces its curves. Our thoughts echo through its halls. We don't just live in space. We are space, folded into itself in a dance of mass and motion. So, if the universe is flat, we live in a grand plane of cosmic possibility. If it's curved like a sphere, we may be looping around inside an invisible bubble. If it's open, we're surfing an endless saddle, heading out into infinity with no round trip planned. Whichever version is true, it's strange, elegant, and beautifully confusing in just the right measure. And that's part of the magic. You don't need to pin down the shape of space to appreciate its mystery. You can simply gaze up, smile at the stars, and know that you're standing on a tiny patch of something grand and curious, a universe with a shape we're still trying to imagine from the inside out. Imagine you're a tiny creature living on the surface of a balloon. You can walk north, south, east, and west along the surface, but you can't dig down or float above it. Your entire world is that two-dimensional skin, curved but seamless. You don't know the balloon is being held by someone with a helium tank. You just know that when you walk straight, you eventually loop back to where you started. This is the magic of curved space. It plays by rules that don't always match our everyday experience, and yet it makes perfect sense once you slip into its rhythm. While we humans live in 3 dimensions of space, curved surfaces in 2 dimensions give us a surprisingly useful way to imagine what our universe might be doing on a much grander scale. Let's start with something simple. A flat surface, like a sheet of paper or a calm tabletop. Geometry behaves in familiar ways. You can draw a triangle, and the angles will always add up to 180 degrees. If you draw 2 parallel lines, they'll never meet. And if you start walking in a straight line, you'll keep going forever, unless you hit a wall or an unfortunate coffee spill. But now, imagine walking on the surface of a sphere, say a planet or that balloon we mentioned earlier. Geometry starts acting a little strange. If you draw a triangle using great circles, like the equator and lines of longitude, the angles can add up to more than 180 degrees. Parallel lines, they don't stay parallel for long. They converge at the poles or drift apart depending on the path. Most importantly, if you walk in a straight line on this curved surface, you'll eventually come back to where you started without ever turning around. No edges, no borders, just a continuous loop. From your limited perspective on the surface, the space around you feels infinite, but in reality, it's finite and curved back on itself. Now, take that concept and scale it up. Imagine our entire universe as a 3-dimensional version of that balloon surface, except instead of curving in 2 dimensions, it's curving in 3, or rather, in a way we can't easily visualize because it curves in higher dimensional space. You and I live inside this 3-dimensional space, moving through it without ever seeing the outside, just like the balloon creature never sees the air around the balloon. In this analogy, galaxies are like dots drawn on the surface of the balloon. As the balloon inflates, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is stretching. This is what cosmologists mean when they say the universe is expanding. It's not that galaxies are flying through space, it's that space itself is growing, carrying galaxies with it. And just like our little balloon creature, if the universe is truly curved and finite, then traveling in a straight line long enough might eventually bring you right back to where you began. You wouldn't fall off the edge of space because there is no edge. The loop closes smoothly. It's a finite space with no boundary, which is a strange and lovely idea. You could go on an infinite journey through a finite universe, never hitting a wall, never running out of room. The balloon analogy also helps us understand something else, why there's no special center of the universe. Just as there's no single center on the surface of a balloon, the universe doesn't have a central point from which everything is expanding. The expansion happens everywhere at once. Every point on the balloon moves away from every other point as it inflates. You and I could pick any spot and call it here, and the view would look the same in all directions. It's worth pausing here to note that the balloon analogy isn't perfect. It's just a model to help our three-dimensional brains wrap around a higher dimensional idea. The balloon's surface is two-dimensional and embedded in three-dimensional space, which we can see and picture. But if our universe is curved, it might be curved in a higher dimensional space we can't observe directly. It's not floating in a larger container. Space doesn't need an outside to curve. It can curve intrinsically by its own properties without reference to anything external. This idea of intrinsic curvature is one of the great insights of Einstein's theory of general relativity. Space, and spacetime more broadly, isn't a passive backdrop. It has shape and structure, and that shape can evolve over time. Matter and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move. It's a beautifully circular relationship, one that governs everything from the orbits of planets to the behavior of galaxies on larger scales. The curvature of space also affects the path of light. In curved space, light doesn't travel in straight lines as we understand them. It follows the shortest path available, called a geodesic. On a sphere, that's a great circle. In our universe, it's a curved trajectory that bends under the influence of gravity and the shape of space itself. That's why massive objects like stars can bend light, a phenomenon known as gravitational lensing. So when we gaze out at the night sky, we're not just seeing objects scattered through flat, empty space. We're seeing a web of light moving through curved space, stretched and bent and shaped by the mass of everything around it. It's like looking at the stars through a slow-moving funhouse mirror, except the distortions tell us something true about the shape of the cosmos. Now, let's return to our balloon one last time. As it inflates, the distances between the galaxies on its surface grow, but the galaxies themselves don't expand. They stay the same size. That's because the expansion of space happens on large scales, between objects not gravitationally bound together. So our Milky Way, our solar system, even our planet and its coffee shops, none of those are getting stretched. The expansion only takes hold in the great emptiness between galaxies. And what's driving this expansion? Well, we now believe that dark energy, a mysterious form of energy inherent to space itself, is causing the universe to accelerate in its growth. It's like the balloon is not just inflating, but doing so faster and faster with every breath. We don't know exactly what dark energy is, but we can see its effects in the way distant galaxies move and how ancient light spreads across the sky. So where does this leave us? It means we live in a space that might be curved, that might be finite yet boundless, expanding yet centerless, shaped by rules that defy our everyday experience, yet make perfect sense in the grand cosmic dance. And all of this, the curves, the expansion, the possibility of looping back to our starting point, can be imagined with a simple balloon, a rubbery metaphor floating through thought space, whispering ancient secrets about a universe that grows not outward from something, but within itself. Next time you see a balloon rising into the sky, give it a little nod. It may be full of helium and squeaky fun, but it also carries within it the shape of something much greater, a gentle curve, a stretch of space, and the quiet idea that maybe, just maybe, the place you're headed is also the place you started, only now you've traveled the universe to get there. Infinity. The word itself feels like it should echo when you say it. It's vast, mysterious, and more than a little intimidating. It conjures up images of endless stars, limitless space, and the kind of concepts that make even mathematicians pause for a moment. But what does it really mean when we ask, is the universe infinite? Is space truly unending, stretching on forever without a final border or wall? Or is there something more subtle going on? Let's start with what we know. So far, everything we've measured about the large-scale structure of the universe suggests that it might be infinite. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, reveal that space is extremely close to being flat, not bumpy like a sphere, and not curved like a saddle, but flat in a geometrical sense. And in the context of general relativity, a flat universe could very well be infinite. If it isn't, it's at least much, much larger than the portion we can observe. That leads us to the observable universe, the cosmic bubble we can see. It stretches about 93 billion light-years across. That's the part of the universe we have access to because light from those regions has had time to reach us since the beginning of the cosmos. But beyond that, it could keep going. There might be galaxies upon galaxies, cosmic structures we'll never detect, entire regions of space that are forever beyond our view. And here's the thing, we can't actually prove or disprove whether the universe is infinite because we are confined to our observational limits. We're like ants on a beach, looking in every direction and seeing only sand. For all we know, the beach stretches across the continent, or maybe it ends a few dunes over in a tide pool full of curious crabs. We just can't see far enough to know. This raises an important point. We don't measure infinity the way we measure, say, the distance to the moon. You can't stick a ruler on space and keep going until the numbers run out. Infinity isn't a number, it's an idea, a concept. And in science, concepts need evidence. That's where it gets tricky. You can never directly observe infinity. You can only look for signs that space shows no signs of curving back on itself, or ending abruptly, or behaving in a way that implies it loops. So far, we've looked in all directions and seen no detectable edge, no sudden drop-off, no cosmic fence. But that doesn't mean such a thing doesn't exist. It just means it's beyond what we can see. The idea of an infinite universe brings with it some very peculiar consequences. If space is truly infinite, then the amount of matter it contains is likely infinite, or at least so staggeringly large that it might as well be. That means an endless number of stars, planets, comets, clouds of dust, and yes, potentially even life. Somewhere out there, in the farthest reaches of a never-ending cosmos, there might be another planet just like Earth. Maybe it has trees that grow sideways, or oceans that sparkle with strange colors. Maybe it has creatures asking the same questions we are, wondering whether their universe ever stops. And here's where it starts to bend the brain a little. In an infinite universe, if matter is distributed more or less uniformly, then the laws of probability suggest that patterns will eventually repeat, which means that somewhere out there, there could be a version of you, or several. Some may be nearly identical. Others might have chosen a different breakfast this morning and accidentally altered the course of their entire day. Now, don't worry, this isn't meant to be unsettling. You're not going to bump into your cosmic twin at the grocery store. These regions are likely so far away that they are forever unreachable. The light from those parts of space will never reach us, even if we wait longer than the age of the universe multiplied by every grain of sand on Earth. Still, the implications are profound. Infinity isn't just a matter of size, it's a shift in thinking. It transforms the universe from something large to something boundless. You no longer have to wonder what's beyond the edge of the map, because there is no edge, just more map forever. Of course, there are good reasons to be cautious about assuming the universe is infinite. We have only a finite sample to work with. And cosmologists remain open to the idea that space might be very large, but still finite. It could curve gently back on itself in a way we can't yet detect, looping through higher dimensions or forming a shape more exotic than we've ever imagined. There's also the question of time. The universe might be infinite in space, but finite in duration. It had a beginning, what we call the Big Bang, and while the notion of a beginning is itself slippery, it suggests that even if the universe is endless in extent, it has not always existed in its current form. Philosophically, infinity challenges the way we relate to the universe. Most things in our daily lives have limits: our time, our energy, the number of cookies in the jar. Infinity breaks that mold. It removes the boundaries and opens up a playground of endless possibility. That can be inspiring or overwhelming, or both at the same time. Some ancient thinkers were deeply uneasy with the idea of infinity. They believed the universe must be finite because actual infinities were just too strange to accept. And even today, some scientists and philosophers debate whether true infinities can exist in the real world, or whether they're just useful abstractions. But whether or not the universe is infinite, contemplating it has value. It stretches the mind, invites humility, and reminds us how small our perspective really is. When you look up at the stars, you're peering into a mystery so vast that even our boldest measurements barely scratch the surface. You're seeing only a local glow, a few lights in the window of a cosmic mansion. And yet, here we are, tiny creatures on a spinning planet, wondering how far space goes. We build instruments to chase ancient light. We invent mathematics to frame the impossible. And we lie awake at night thinking about what lies beyond the last star we can see. Maybe the universe is infinite. Maybe it's not. Either way, it's more than enough. More than enough to fuel our questions, our stories, our science, and our dreams. More than enough to remind us that we're part of something truly immense. And the most wonderful part of all? You don't have to know how far it goes to feel at home in it. You're already woven into its fabric, a flicker of thought on the edge of the observable, glowing softly in a cosmos that may never end. There's something irresistible about the idea of an edge. We grow up with edges, walls, fences, sidewalks. Everything we encounter seems to stop somewhere. So when we think about the universe, it's only natural to imagine it must stop too. Surely, after some truly staggering distance, space must come to an end, like the final room in a very big mansion, or the edge of a massive tabletop hanging over the abyss. But here's the twist. Space doesn't actually need an edge. It can be finite in size without having a boundary at all. And that's where things get beautifully strange. Let's start with something simple. Picture the surface of Earth. If you were to walk in a straight line in any direction, you would eventually circle back to where you started. You wouldn't fall off anything, you wouldn't hit a wall, and you wouldn't find a signpost reading, "End of Earth, please turn around." The surface is finite but unbounded. It loops back on itself in a seamless way. Now take that idea and expand it to three-dimensional space. Imagine living inside a volume of space that wraps around itself in much the same way the surface of a globe does in 2 dimensions. If you could keep moving forward in a perfectly straight line through this space, you might eventually return to your starting point, having never encountered a wall, cliff, or any kind of edge. This kind of space is not science fiction. It's a perfectly valid model in cosmology. It's called a finite, unbounded space. It sounds like a paradox at first, but once you understand the geometry, it clicks into place. Space can be shaped in such a way that it closes in on itself, forming a complete volume without ever needing to end. One of the classic shapes used to illustrate this idea is the torus. Imagine a donut, not the jelly-filled kind, but the smooth, round kind with a hole in the middle. The surface of the donut is 2-dimensional. You can walk around it without leaving the surface, but it has no edges. It loops back on itself both horizontally and vertically. If you're an ant walking on the donut, you can go forever without ever hitting a boundary. Now imagine a 3-dimensional version of that, where space loops in multiple directions. This doesn't mean the universe is shaped like a pastry, but the torus helps us visualize how space might behave if it were finite and without a border. You could start at one point in space, travel in a straight line, and after a very, very long time, find yourself right back where you began, like a galactic boomerang. Another helpful analogy comes from video games. In certain classic games, if you move your character off the edge of the screen on one side, they reappear on the opposite side. It's not that there's an invisible tunnel, they've just looped around on a map that wraps back on itself. These are two-dimensional versions of a toroidal space. The game world is finite in size, but the edges don't behave like real-world walls, they connect. In theoretical cosmology, this idea is more than just playful musing. Some models propose that the universe could have a topology, its fundamental shape, that loops back in subtle ways. We might not notice these loops unless we looked far enough and in just the right direction. There's even been speculation that if the universe is small and curved just right, we might see repeated patterns in the cosmic microwave background, like mirrored wallpaper left behind from the Big Bang. So far, we haven't found any clear signs of this repetition, but the idea hasn't been ruled out completely. The deeper truth is that the universe doesn't need an outer surface or a surrounding void. That's a very human way to look at space, as if there's something sitting inside something else. But space isn't a thing embedded in a bigger thing. It is the thing. It's not like a balloon floating in air. It's more like the entire balloon itself, with all of us on its surface, unable to step outside and look in. Even if the universe is infinite, it still doesn't require an edge. Infinity isn't a place, it's a property. Saying the universe is infinite is like saying numbers never stop. You don't need to find the last number to know that one doesn't exist. Likewise, you don't need to locate the edge of space to know there might not be one. Edges also create philosophical headaches. If there were an edge, what would be beyond it? More space? Something else entirely? A blank nothingness that sits awkwardly waiting to be defined. The moment you introduce an edge, you introduce a paradox. If there's something beyond, then space hasn't really ended, and if there's truly nothing, then how can it be said to exist at all? By contrast, a universe without edges avoids this confusion entirely. It just is. You can keep moving forever, or you may come full circle. There's no edge to fall off, no cosmic warning signs, and no need to define what's beyond the beyond. This doesn't mean we'll never stop asking about boundaries. Our brains are wired to think in terms of containers. We like beginnings, middles, and ends. But the universe doesn't seem to care much for our mental filing cabinets. It stretches, curves, and possibly loops, all without offering a clean border to sign off on. Interestingly, even if space has no edges, time might. Our universe had a beginning, at least from our perspective, with the Big Bang around 13.8 billion years ago. That's not a point in space, but a point in time, a moment when space itself began expanding from an earlier state. Asking what came before the Big Bang is like asking what's north of the North Pole. It's not that the question is meaningless, it's that our usual coordinates stop working. All of this paints a picture of a universe that's far more subtle and strange than a giant box. It's not an object you can lift the lid on or peek around the side of. It's more like a melody that plays itself forward, wrapping around dimensions and humming through time with no final note, no ending chord, just an endless variation. And in that melody, there are no hard edges, only connections, curves, and continuations. Whether it loops or stretches infinitely, the universe doesn't close off like a room. It opens up like an idea, not bounded by walls, but shaped by relationships, gravity, light, motion, time. So if you've ever imagined a spaceship sailing bravely toward the edge of the universe, picture this instead. A long, quiet journey that never finds a cliff, only more stars, more questions, and more space. Not because the universe goes on forever necessarily, but because it never had an edge to begin with. Before there were stars, before there were galaxies, even before atoms had properly settled into their roles, there was a glow. A soft, uniform light spread across the universe like a warm fog, stretching in every direction. It wasn't a spotlight or a flash or fireworks, it was quieter than that, gentler, like the first rays of dawn seeping through a window before anyone's had a chance to open their eyes. And some of that light is still with us today. We call it the cosmic microwave background, or CMB for short. It's not just the oldest light we can see, it's the oldest light anyone can see. A whisper from the very early universe, still drifting gently through space, passing through galaxies, stars, planets, and sometimes, with the right instruments, into our detectors. To understand where this light comes from, let's go back in time, way back. About 13.8 billion years ago, the universe began in a hot, dense state, a singularity of seething energy and unfathomable temperature. In its earliest moments, space expanded rapidly, spreading out the energy. As the universe grew, it cooled, not quickly but steadily, like a cosmic kettle slowly taken off the stove. At first, the universe was a blinding soup of particles and radiation. Photons, the particles of light, bounced around constantly, trapped in a fog of charged particles. Electrons and protons whizzed around separately, and light couldn't get very far before being scattered in a new direction. Imagine trying to shine a flashlight through a dense cloud. That's what the universe was like for its first few 100,000 years, opaque, chaotic, full of restless motion. But then something magical happened. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This moment is called recombination, and it changed everything. With fewer charged particles to scatter off, light was suddenly free to travel. The fog lifted, the universe became transparent, and the first light broke loose. That ancient light, set free across the cosmos, has been traveling ever since. It fills the universe in every direction, stretched out by billions of years of cosmic expansion. Once a searing blast of ultraviolet energy, it's now cooled to a gentle microwave hum, a whisper instead of a roar. But it's still there, all around us, passing through your room this very moment like a soft, invisible breeze from the beginning of time. We first discovered the CMB almost by accident. In the 1960s, two radio astronomers were using a large horn-shaped antenna to study radio signals. They kept detecting a persistent background noise, no matter where they pointed their antenna. They cleaned the equipment, double-checked their math, and even removed some pigeons nesting in the device, just in case. But the noise remained, steady, uniform, and strangely cosmic. What they had stumbled upon without realizing it at first was the afterglow of the Big Bang. It was the cosmic microwave background, predicted by theory and now detected in all its subtle glory. That faint hiss on their radio signal turned out to be a window into the infant universe. Since then, scientists have mapped the CMB in astonishing detail. Space missions have given us high-resolution pictures of this ancient light, and what they revealed is more than just a glow. It's a cosmic blueprint, a snapshot of the universe when it was less than 500,000 years old. At first glance, the CMB looks incredibly uniform, the same temperature and brightness no matter which way you look. But zoom in closely and you'll see tiny ripples, little warm and cool spots, just a few millionths of a degree different from each other. These gentle ripples aren't imperfections, they're the seeds of everything, tiny differences in density that over billions of years would grow into stars, galaxies, and eventually you sitting here listening. Those slight variations are clues. They tell us how matter was distributed in the early universe. They reveal the physics of the cosmos at its birth, and they let us test theories about how space and time unfolded in the first few heartbeats of creation. Even the shape of the universe leaves its fingerprints on the CMB. The way those ripples stretch and move carry information about the environment they travel through. In the same way, the CMB carries encoded messages about the shape, size, and ingredients of the universe. It's light as data, photons as historians. And there's something deeply soothing about imagining that glow, a soft, gentle wash of ancient light, not blinding or fiery, but calm and even, not one you can see with your eyes, but one that's always present. It's like the universe's own lullaby, still playing after all these years. If you could tune in with the right kind of radio, you'd hear it everywhere, not as a song, but as a faint, static warmth, a constant, low-level presence woven into the very fabric of space. It's the closest thing the universe has to a baby poto, a snapshot of its earliest moment of clarity, and it's still whispering to us long after the stars were born, long after galaxies spun into shape, long after Earth began its slow dance around the sun. That light has outlived generations of stars, crossed unimaginable distances, and arrived here, in your lifetime, ready to tell its story. In a universe filled with mystery, the CMB is something solid, something we can measure, map, and understand. It reminds us that we don't need to chase the edges of space to learn about its beginning. Sometimes the answers are already floating all around us, waiting patiently in the glow. Where does space stop? It's the question that brought us here, whispered softly at the beginning, like someone asking if the sky has an end. And after wandering through galaxies, curved dimensions, cosmic microwave whispers, and the edges that may or may not exist, we find ourselves gently circling back to where we began, still wondering. We've learned that space doesn't behave like a room or a box or a stretch of road. It doesn't need walls to be complete. It can be infinite or finite and unbounded. It can stretch, loop, curve, and fold in ways our minds are only beginning to understand. It can even carry galaxies away from us faster than light, not because they're moving, but because the space between us is growing. We know that there is a limit to what we can observe, a cosmic horizon beyond which light has not yet reached us, but we don't know what lies beyond it. Maybe the universe keeps going forever, or maybe it folds back on itself in a gentle arc we'll never see. Perhaps our universe is one bubble among many, drifting in a higher dimensional sea. Or perhaps such ideas are just poetry, beautiful but unreachable. What we do know is that space is not empty. It's alive with structure and subtle energy. It stretches with time. It carries the light of ancient stars and the hum of the Big Bang. It has no center and, as far as we can tell, no end. And still, questions remain. Is the universe infinite or just very large? Is it curved, flat, or something else entirely? Is it one of many or all there is? And if there were an edge to space, what would be on the other side? We may never find all the answers, but that's not a failure. It's the heartbeat of science. The beauty of the cosmos isn't just in what we know, it's in what we don't. It's in the quiet courage of looking up and asking anyway. The search continues, as it always has, through telescopes and equations, through gentle dreams and midnight thoughts. Every photon we catch, every map we make, every model we refine brings us a little closer, even if the destination keeps shifting like the stars. Maybe that's the whole point. maybe space never stops, not because it's infinite in size, but because it's infinite in mystery. Maybe it doesn't have to end for it to matter. Maybe it just is, sprawling quietly in all directions, an invitation, not a boundary. Think about it for a moment. We're sitting here on a small planet, orbiting an average star in a galaxy that's one among trillions. And yet we've managed to measure the afterglow of creation itself. We've traced the paths of light that began their journeys before Earth existed. We've built mathematical frameworks to describe how space bends and time flows. We've asked questions that reach across billions of years and light years. And all of this from creatures who, in the grand scheme of cosmic time, have only just opened their eyes. Humans have been looking up at the stars for thousands of years, but we've only understood what they really are for about a century. We've only known the universe is expanding for less than 100 years. We've only seen the cosmic microwave background in detail for a few decades. In that incredibly short time, we've learned that space is a fabric, not a void, that it can stretch and curve, that it has a history, a structure, perhaps even a shape we're still trying to understand. We've learned that looking out into space is looking back in time, that the universe is older and larger than we initially thought, that some galaxies are moving away from us faster we'll never see them again. We've learned that there are horizons we cannot cross, not because of technological limitations, but because of the fundamental nature of light and time. We've learned that the very emptiness between stars hums with quantum energy, that even nothing is something. And perhaps most importantly, we've learned to be comfortable with uncertainty, to sit with questions that may never have answers, to appreciate mystery not as a frustration, but an invitation, because the universe doesn't owe us explanations. It doesn't need to make sense to our human minds, evolved to navigate forests and savannas, not cosmic voids and curved spacetime. Yet here we are, using those same minds to reach across the universe, to touch, if only intellectually, the very edges of existence, to ask whether there are edges at all. That's remarkable, that's beautiful, that's worth celebrating, even if, especially if, we never find a final answer. So, does space bend? Maybe, maybe not. Maybe the question itself is flawed, born from our human need to put boundaries on things. Maybe space simply is, neither ending nor infinite, but something beyond those categories, something we're still learning the language to describe. What we can say with confidence is this: the observable universe, our cosmic bubble, is vast beyond comprehension, 93 billion light-years across, filled with 2 trillion galaxies, each containing billions or trillions of stars. That's what we can see, and it's more than enough to inspire wonder for 1,000 lifetimes. Beyond that, there might be more of the same, stretching forever. There might be a gentle curve that brings everything back around. There might be other universes, other dimensions, other realities we can't even begin to imagine. Or perhaps there's something else entirely, something so strange that we don't yet have the concepts to think about it properly. And you know what? That's okay. Because the journey of discovery isn't about reaching a destination. It's about the questions we ask along the way, the tools we build, the understanding we gain, the humility we develop when we realize how much we don't know, the wonder we feel when we catch a glimpse of how it all fits together. Every time we look up at the night sky, we're participating in something ancient and profound. We're continuing a conversation that began the first time a human looked up and wondered what those lights in the sky were. We're part of a long chain of curious minds, reaching across generations, building on each other's insights, slowly piecing together the story of existence itself. And the story we've uncovered is magnificent. A universe that began in a hot, dense state nearly 14 billion years ago, that cooled and expanded, forming the first atoms, the first stars, the first galaxies, that continues to evolve and change, even now, even as we watch. A universe that might be infinite or might curve back on itself, that might be one among many or all there is, that definitely doesn't have an edge in the way we usually think of edges, but might have boundaries of a more subtle kind. It's a universe where space itself is a dynamic thing, responding to mass and energy, expanding and stretching, carrying galaxies along for the ride, where space and time are woven together into a single fabric, where the fastest thing in existence, light itself, becomes a messenger from the past, bringing us news from billions of years ago. It's a universe that operates on scales both impossibly large and unimaginably small, where quantum fields fluctuate in the vacuum of space, where black holes warp spacetime so severely that not even light can escape, where galaxies collide over millions of years in slow-motion cosmic dances, where new stars are born and old stars die, recycling their material into the next generation. And somewhere in the middle of all that, on a small rocky planet orbiting a yellow star in the outer reaches of an ordinary spiral galaxy, there are beings who have figured out how to ask questions about it all, who have learned to read the language of light and decode the messages written in starlight, who have built telescopes and satellites and mathematical frameworks to understand what they're seeing. That's us. We're part of this story, not separate observers looking in from the outside, but participants in the cosmic drama. We are quite literally the universe becoming aware of itself. We're made of atoms forged in the hearts of stars. We're built from the same fundamental particles that make up everything else. We breathe oxygen created by ancient bacteria and breathe out carbon dioxide that plants will use tomorrow. We're connected to everything, woven into the fabric of existence. And from our small corner of space, we've managed to glimpse the shape of it all, to see how the pieces fit together, to understand, at least partially, how we got here and what's happening around us. That's not nothing. That's extraordinary. So as you drift off tonight, or whenever you're listening to this, let yourself feel that connection. You are part of an expanding universe. You are made of stardust. You are a temporary arrangement of atoms that happens to be conscious and curious. You are, in a very real sense, space itself folded into the particular shape of a human being for a brief moment in cosmic time. And whether space ends or not, whether it's infinite or finite, curved or flat, one universe or many, you are here now, part of this moment in cosmic history, part of the grand unfolding, part of the question, and in your own small way, part of the answer too. The universe might not have edges in the traditional sense, but it has given us boundaries to work with, horizons to contemplate, limits that define what we can know and inspire us to reach for what we can't. And maybe that's enough. Maybe the edges we need aren't out there in space, but in here, in the boundaries between the known and the unknown, between certainty and mystery, between the comfortable and the wondrous. So rest easy. Let your mind drift like a galaxy in expanding space. Let your thoughts float gently like photons on their long journey from distant stars. And know that you don't need to understand everything to be part of something beautiful. The universe is still here, still humming quietly with energy and possibility, still stretching, still evolving, still full of secrets waiting to be discovered. And tomorrow, or next week, or next year, there will be new questions to ask, new discoveries to make, new wonders to uncover. But for now, for this moment, just rest, just be, just exist as a small, precious part of an incomprehensibly vast cosmos, a cosmos that might not have edges, but definitely has room for you. And if you're interested in more content like this, gentle explorations of cosmic questions that help you relax and wonder at the same time, I'd love to see you again. There are so many more questions to explore, so many more mysteries to ponder. Until then, wherever you are in the world, whatever time it is for you, I hope you sleep well. I hope you dream peacefully. And I hope when you look up at the stars tomorrow night, you'll remember that you're not just looking at space, you're looking at home. Thank you for spending this time with me. This is Alara signing off from the Late Night Science Channel. Sweet dreams, fellow wanderer.